Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Are you ready in there? Is this working now? Terrific, thank you. Good morning. My name is Gursharan Sidhu. I'm very new to MSR. In fact, I just joined in July, prior to which I was in Windows Networking, where I was general manager. Prior to Microsoft, I did a voice over IP company that I founded. But relevant to our conversation today, before doing my startup, I was at Apple Computer for about 15 years, starting in the early 80s, and had the good fun and enjoyable time of being in on networking technologies and desktop publishing from almost its inception, and building those capabilities for the Macintosh world, and in fact for MS-DOS machines also, though most people, I think, have a certain level of amnesia at Microsoft about that. It was a very successful run. And I guess having created many of those technologies, it was considered appropriate that I host Stuart Cheshire, who has been at Apple for quite a while since he did his PhD at Stanford. And prior to that, he got his undergraduate degrees with great distinction at Cambridge. Stuart's talk is about zero configuration networking, and I will give a rather long introduction today. Why? Because I think the roots of what he's going to talk about are in my work from a period that most of you are not aware of, were probably not doing any networking, didn't even know networking technology existed, or you were too busy in elementary or high school or wherever. And so there is a kind of a sense of, we just thought of everything in the last 5 years, and it would be good to know that that's not true. And that, in fact, the kinds of things that motivate us so strongly at Microsoft, the idea of customer-focused design, customer-driven design of products, capabilities, and features, have been motivating entities for a rather long time. So let me take you back to some early days, 1983, in fact. As far as desktop computers are concerned, there were really only two kinds of machines worth bothering with. One was the Apple II, although its siblings, the Apple III, and Lisa had made valiant attempts to seize a little corner of the desk, but had not quite succeeded. And then there was IBM's PC, introduced about in that same time frame. Networking was exceedingly expensive. Local area networking technology interfaces cost about the same as the desktop computer. Indeed, modems cost about the same as a desktop computer did in those days. So the scene was vastly different. Cost was a major issue. Second, value. What was it worth it? Why should you do a network? Well, guys, the internet didn't exist, nor did the notion of value from things such as the internet understood at all, except in some parts of the research community. The whole business of, why should we do networks was focused even then on certain small startup companies building things for enterprise-oriented kinds of applications in departments and whatnot, building disk servers and whatnot. However, a major segment that Apple focused on, which was the consumer, we used to use the phrase the rest of us, was completely, totally unserved. And that world is characterized by a tremendous aversion to complexity or difficulty. People, consumers, don't want to be gadget freaks. Some of them are, but most just want to do their business. They want to plug things in and have them work. That's why the appliances-oriented industry had evolved. And Steve Jobs drove the Macintosh notion towards an appliance, a machine you plugged in, switched on, and it just worked. Configuration was a bad word at Apple. I happened to be at Apple at this time and convinced Steve that we could do the same thing with networks, and that led to the work on AppleTalk. What were the driving notions that we built into AppleTalk? And I'm telling you these because these are all customer-driven, and we talk a lot about customer-driven design in Microsoft. One was the user should never have to configure anything. Network addresses exist for the benefit of network devices, not for the user to mess around with. So x.y.z.w was considered heresy to impose upon a user. Two, so you get the notion, users shouldn't configure anything. Two, users understand things that have names. And those things don't have to be devices. There are services they use. So the user wants to deal with named entities, and by invoking a name, they should be able to just use it. Okay? And three, it had to be cheap. And it's something in which, when things break down, the thing heals itself. So notions of late binding, which were not popular at all in computer networking at that stage, were things that we embraced. The notion of getting a machine or a device to automatically find an address by guessing one, checking with others on the network, see, is anybody using this? If no one's using it, keep it. If not, pick another one and try it out, which are now at the heart of all dynamic addressing schemes with all kinds of RFC and cryptic numbers assigned to them. We came up with those notions at that time. The notion of giving something, a service, a name rather than a device was the second thing proposed, and the device would give itself a name, and use of link level discovery mechanisms to find that named entity and therefore discover its address and then bind with it were brought into play. And this was expressed in very nice, clean things like the chooser and so on and so forth. And it was immediately embraced. And I should give you one piece of data. When the laser writer was introduced, which was the first kind of other device than the Macintosh that embraced this approach, the sales of the laser writer in the first or the second year hit $1 billion. And $1 billion used to be something in those days. One, it did some wonderful things, and two, it was very, very easy to use. You just plugged it in, turned it on, and it worked. And a whole ecosystem started developing around this, and this became kind of the hallmark of what was done there. Now, people tend to say this only worked on a single segment. That's all nonsense. It worked across very large multi-segment networks. Apple's own corporate network, you could print on a printer in Sweden from Cupertino, and all those constructs were there. Now, clearly, we didn't have the infrastructures that exist today, but what existed there, we made all this work, and pretty damn well, and in products, not in laboratory prototypes. Today, we have far greater riches. The internet, IP, bandwidth is prolific. It was not then. And so it is completely appropriate that taking notions and ideas from those days and their value and expressing them in far more powerful ways today should happen and should be done. And that from reading the draft of the book that Stuart sent me and my own interactions with him over the last 2 years, is part of what they've done, and there's definitely more. Now, Stuart in here mentioned something, and with that, I will close my introductory remarks and turn the podium over to him. He says, Bonjour is not simply a rewrite of AppleTalk NBP. There are many things that NBP got right. NBP is name binding protocol, which is a fundamental to AppleTalk. And Bonjour brings those properties to IP networking. I'm gratified that he feels we got a few things right in the hoary days of 1983. Equally, I'm interested in knowing what we did not get right, but because all learning comes from what one didn't do right and what they did do right in Bonjour. So I'm looking forward to learning something new today. In reading through the draft of his book which is authored with Daniel Steinberg, it's quite impressive how truthfully, you have stuck to the tenets that I kind of outlined that, we built Apple's networking and connected systems on and expressed them in wonderful new ways. And with that, I turn the podium over to Stuart, and he's going to also do some wonderful demos of real plug and play.
Thank you, Gershran. I shouldn't give the impression that I think AppleTalk got a lot of things wrong, but it was done in a different era. It was done 20 years ago, and these days we have faster CPUs and more memory and higher bandwidth, and we have the opportunity to do things. And of course, we have the internet that scales to a much larger scale Back in the 80s, a network of 10,000 machines seemed unimaginably ambitious. And of course, 20 years have passed since then. So this presentation I'm going to give, I've borrowed some of the slides from a tutorial I gave at the O'Reilly Open Source Conference last year. That was a 4-hour tutorial, so I won't be showing all the slides. But that's why it's got the little O'Reilly animal and the O'Reilly name on the slides. And I started that with a quote from Tim O'Reilly. Tim O'Reilly has been a big fan of Bonjour, or Rendezvous, as it was a couple of years ago. He's not a fan of the name, he's a fan of the technology. And that's why he asked me to write a book. And that was a new experience for me. I haven't done that before, but that book should be out in the bookshops before Christmas. I wish I'd had a few ready to hand out here, but it's not quite finished yet. It'll be another month or two. So Tim's a big fan. And you may know that Tim is not just a book publisher. Tim hosts a bunch of conferences, and he's really interested in technologies that he sees as enabling people to do interesting things and collaborate in interesting ways. So my vision here was you should be able to buy network appliances and plug them in like the way you plug in a table lamp. You plug them in and you turn them on and they work. And that's it, no excuses. And there's no reason IP can't do that. Everybody assumed that it's naturally got to be hard, and IP addresses and subnet masks and DNS servers and all this kind of nonsense. But AppleTalk kind of gave us a proof by example that networking doesn't have to be hard. And I'll talk a bit more about that in a minute. So when I left Stanford, I kind of got a reputation for being vocal on mailing lists and complaining about the really lousy state of ease of use for IP. And the IETF area directors decided to form a new working group and made me the chairman of it, which I don't really remember volunteering for, and that was a bit of a hairy experience. But that was what I did, and I went through the trial by fire of the IETF process there, and that was really not a lot of fun. But we finished 5 years later with an RFC for something that Peter Ford and I had discussed on a napkin in a bar in 1998. So not really a glowing endorsement to the IETF, but that's what happened. We call it ZeroConf because this is not just about home networking, and it's not about making administration easier. It really is about getting rid of the configuration, because anything that can be configured can be misconfigured. And it is a really, really strong temptation for engineers and everybody, I think, to keep adding options and choices to things. And if you're not quite sure which to do, and some users might want A and some users might want B, then the answer is, oh, well, we'll let the user decide. And you end up with these user interfaces that are just full of rows and rows of checkboxes and radio buttons and menus, and sometimes then you have tabs across the top, so you have multiple pages of these things. And every individual option by itself doesn't seem fatal, but when you put the whole collection together, you just crushed the user under this incredible burden of decision-making that they're not qualified to make. They don't have the time to learn about it. It's not that they're not smart enough, but people have got lots of things in their life, and they've got finite mental capacity to deal with complexity, and they've got to parcel up their time and their mental capacity between the things that are interesting. And if you take too much of that pie chart for your product, then it's not going to be of interest to the consumer. They're either not going to buy it, or they're going to buy it and it's going to sit in a drawer and be unused. What is a ZeroConf network? Well, we fully accept that a network the size of the internet, or even the network the size of a corporate network, needs paid staff who know how to run it and know how to manage it, and they have policies and they run the wires. And we're not trying to replace that. But where the area that is terribly badly served today is a desktop with a few devices, the home user. Maybe as simple as a computer and a printer and an Ethernet cable. With wireless, maybe even no cable at all. those are the networks where it would be nice to be able to use IP, but if we can't rely on IP to work properly because the user may not have configured it right, then it makes the market for the products that do that pretty small, because even if you could sell them, you'd be crippled by the return rates and the support calls of people who couldn't get it to work. So hooking up to a printer is one example, and there's a reason that most printers are USB today. And it's not really because a USB chip is cheaper than an Ethernet chip. That's a very small difference these days. The real difference is that if you made an Ethernet printer, people couldn't get it to work. And I find that very sad, because having a network accessible printer is really much, much more useful. If you're sitting on the sofa with a laptop with a wireless network, having to get up to plug into the USB cable to print is a bit of a hassle. So if we really could make IP as easy to use as USB, that would be a big benefit for people. Do we have a question back there?
Yes. You mentioned wireless connectivity. Once you go wireless, you need something to stop my next door neighbor from using my printer or file server, and vice versa. And get much harder.
Security is a very interesting question, and we could literally have a whole hour-long talk just on security. And there is definitely a conflicting goal there, which is ease of use says that I should be able to just plug in and have it work. And security says that you should not be able to just plug in and have it work. So they really are two goals pulling in opposite directions. And what I'm focusing on in this talk is solving the critical ease of use problem. Once you've made it possible to discover the printer, then end-to-end security, encryption, authentication, and authorization are definitely very important features to have. But if you can't even find the printer in the first place, then all of the rest of it doesn't really matter. This is not just aimed at desktop PCs with gigabytes of RAM and multi-gigahertz processors. This is really aimed at little devices, very low cost, with very constrained memory and very limited processors. So a lot of the kind of heavyweight solutions that we can prototype on our desktop machines become limiting when you try to put those into very low-end devices. And I've got a couple of things in my bag here, which I'll show you later, that I think are really pretty extreme examples of how low-end you can go with IP. And I'm a big believer in simplicity. Whenever you have protocol designed by a group of people, there's always a much bigger tendency to throw features in, and there's a lot of resistance to taking things out. So things tend to accrete complexity over time, and it's the death of 1,000 cuts kind of result, which is that each individual feature doesn't seem too bad, but at the end of the day, you've got this thing that's so burdened down that it's complicated to implement, it's difficult to debug, it's difficult to test, because the testing matrix has so many different options in it. So I'm a big believer in simplicity, and I'm a big believer in making trade-offs and deciding, well, we could have an SQL query engine, but we won't. We'll have something much simpler, and accept that there are some things you can't do with the simpler thing, but what you can do with it is get it widely deployed very easily, ubiquitously, and have it work reliably, so that you don't need to have a massive testing matrix. You can actually take two products from different vendors and have a reasonably high expectation they will in fact work together. One of the analogies I always make is when you buy hi-fi components. Every CD player has those red and white analog RCA connectors on the back, and you plug that wire into your amplifier or the back of your television or whatever you're using, and sound comes out. Right? Nobody has ever had difficulty configuring that wire because its subnet mask was set wrong, or it was using a different voltage or something. And we really need networking to be as easy as that. You plug it in and it works. This is a protocol design principle I learned at the IETF. A design is not complete when there's nothing left to add. It's complete when there's nothing left to take away. This is actually not really a networking design principle. It's from, I'm forgetting the name, a French guy, Saint-Exupéry. And it's actually, the quote relates to aircraft design, that an aircraft design is only complete when there's nothing else you can think of to take away. So one question I will touch on is why IP? And when I started giving these presentations 5 years ago, this was a harder sell. I'm actually expecting in this audience today, this will not be a difficult sell. But looking at the situation 10, 15 years ago, there were all these competing wide area protocols. And what has happened since then is they've all died. TCPIP is the clear winner, and things like AppleTalk and NetBIOS that were good in their day are not going to compete, because the world doesn't need 3 or 4 or 5 networking protocols. It needs one, and it's clear that the one is IP. So let's look at local area. The back of our computers have all these connectors on. And the good news is those have pretty much all become obsolete as well. But now look on the back of my computer, it's still full of a whole different set of connectors. They're different voltages, different plugs, different cables, different protocols. And what are we, as an industry, what is the networking and the communications and the peripherals industry doing about this? We're adding even more different ways of connecting things to our computers. And it's not just that the connectors are different, because connectors are easy to manufacture. It's that all the layers of software on top of that is really difficult to implement and debug and get right. And this is why we can transfer files over IP. And if you plug 2 computers together with the USB cable, you can in principle transfer files. But I don't know many people who've managed to do it. And you can do it over Bluetooth if you've got the Bluetooth file transfer software and you know how to use it. And the reality is today, most people still use a floppy disk. And if they don't have a floppy disk, they burn a CD, or they use the USB flash memory keychain drives, which is kind of the spiritual equivalent of the floppy disk for the 21st century. But it's still sneakernet. And this is pretty sad. It's a sad statement on what the networking industry has achieved when we have gigabit Ethernet on cheap laptop computers, and sneakernet is still the preferred way of getting data from A to B. So the problem we need to solve here is we've got really unprecedented bandwidth coming out of the back of our computer, and it is idle 99.99999% of the time because half the users never even connect a cable to it. So what do we need to do to make IP as easy to use as AppleTalk was, or as USB is? And this is the problem I set out to solve. And I set out to solve it in the simplest way possible. At the end of this talk, if you walk away thinking, well, that was all really obvious, I didn't see anything clever there, then you've really got the point. Because I'm not setting out to do something that blows your mind and you think, that's such genius, I could never have thought of that. Really, these solutions are the very obvious, straightforward solutions, and for some reason, the people who worked on networking just didn't think they were interesting enough to solve. They were off optimizing TCP for interstellar connections with multi-hour round-trip delays or something, and they were not worrying about the guy at home who can't print. So there are 3 things you need for IP networking. You need an address, obviously. You're not going to do much IP networking without an address. Having got an address, people don't want to be typing numbers in, so you need some kind of naming service. And that's good. But you still need to know what name to type in, and you need to type it correctly. So the next step would be if you didn't even need to know the names in advance, if you could just browse and discover what was being offered on the network. So these are the 3 legs of what I call zero configuration networking, what Apple called rendezvous, and now Bonjour. And one question I'm asked is, if this stuff is also good, how come I haven't heard about it? Because pretty much every network printer that's been sold for the last 2 years runs this software. But most people are completely unaware of that. And the reason for that was really an Apple marketing mistake. We picked a name, Rendezvous, which is a really, really good name for this technology. In fact, it's such a good name that somebody else picked it first and registered the trademark. And we spent 2 years ensnared in that, unable to license the trademark to anybody else making products. So all the printers shipped with nothing on the box to say what it was they did. And for me, that was a big pity, because it became the best kept secret in networking. So addressing, very simple, borrowing from what AppleTalk did. You pick a random number and you send an ARP request. And for those of you who don't know, ARP is the way you map from an IP address to the Ethernet address for that address. And you send a broadcast saying, who has this address? Well, if nobody answers, well, then nobody has it. So you can have it. So that's how you assign addresses. There's a range assigned by IANA for this, 169.254. And within that range, it's a free-for-all sandbox where anybody can grab any address they want, providing they follow the rules of checking it's in use before they go and stomp all over some other device that might already be there. This is now published as an RFC. And you guys have probably all seen this, because this has been in macOS and Windows since 1998. And it's the thing you see when the network is screwed up, and you say, one of those 169.254 addresses again, the computer's not working. And that's a bit disappointing for me, because sort of people came to sort of curse these things. But the reason you get that impression is that it's the first layer of a foundation, and when nothing else is built on top of it, there's nothing to use it. So it's just kind of there doing nothing. And the rest of what I want to talk about is what we built on top of that. So we have an address. The next thing we need is a name. And NetBIOS naming does this. There are other solutions that have done this in the past, but we need a mechanism that fits in with the way TCPIP works, something we can be using moving forwards. And again, we followed a principle of extreme simplicity. With the link local addressing, this is not a substitute for DHCP. DHCP is great if you have a DHCP server. It's the safety net for if you don't. And likewise here, this is not a substitute for the existing DNS system. The existing DNS system is a wonderful global distributed database, probably the biggest distributed database that mankind has created. But if you don't have a DNS server, then we want something more than the device just falling on its face and not knowing what to do. So this is the same packet format as a DNS query. It's the same naming syntax, the same record types. As much as possible, everything exactly the same. It's just if you don't have a DNS server to ask, well, you ask everybody. You multicast it to all the devices on the local network. Each device has a little responder, very much analogous to the old AppleTalk NBP responder that every device had. And if it sees a query for its name or for some other name that it knows, then it sends an answer. And the answer is a standard DNS format answer. So that's it. It's a very, very simple solution. You can implement the client side of this in about 5 lines of code. You take your existing DNS client, and it builds its query. And right before it's about to spit that UDP packet out onto the wire to the DNS server, you have a look, and you see if the name ends in .local. And that's the key that we use to tell the DNS client software, this is not a global DNS name. This is only locally significant. And you just overwrite the target IP address and port number that you're sending it to be the multicast address instead, and then you send it. And the response that comes back is a standard response, so the DNS client doesn't even really know that it's done a multicast. It doesn't need to know what multicast is. All it knows is that it talked to this funny DNS server with address 224.00251, and it got an answer. So that's how you can look up names. And that's been around for a few years as well. And I'm not going to bother doing a demo of that because I'm sure you can all imagine how that works. The next step is raising the bar, because...
I'm sorry, real quick on the DNS though. Where is this cached? Is there some centralized repository?
There is no centralized repository at all. Each device knows its own name, and each device maintains a cache. So when I plug in some of these devices later, this machine sends out a multicast query, and whichever one knows the answer responds. And it's designed for ad hoc networks. It's designed, frequently one of the biggest uses of this is in bootstrapping and setting things up. You get the product out of the box and it's unconfigured and it doesn't know anything. And the first thing you do is connect to it to configure it and set it up. So in some ways that's a fairly unglamorous use for the technology because it's only used for about 5 minutes. But those 5 minutes replace several hours of struggling if you didn't have this.
You're trying to do, if you're in a browse situation, some other device in the network has been turned on for the first time. broadcast its name? How are you going to browse for this device by name?
I will come. The question was what happens when devices are turned on, and a little bit later I'll explain. But in brief, devices issue queries when they're interested in things. Devices newly connecting to the network issue unsolicited responses. They issue announcements. And that way you avoid the need to do rapid polling to find out what's on the network. So it's kind of driven from both ends. There's another question at the back there.
Are you able to comment on the scalability of this game? Because everything you mentioned is kind of broadcast.
I want to repeat the question.
Yes, the question was about the scalability of this. And I will talk about how this scales. And the short answer right now is it scales by transitioning over to the existing unicast DNS system that we already have. And I know that Active Directory has some kind of shades of this in it as well, in that it can answer certain queries using DNS format packets. The multicast DNS is explicitly designed for the case where you don't have infrastructure. And if you don't have infrastructure, that means it's a small network. Or at least if it's a big network without infrastructure, you've got to be willing to spend some bandwidth. It's a trade-off. You can have administrators set it up, or you can do everything with multicast. And multicast has the nice property that it's zero configuration, but it's not free, which is why you wouldn't want to run a network of 10,000 devices this way.
Since like in the example you mentioned in the beginning, you said you can actually use this game to ask a printer in another country to print. I'm just wondering how this is doing.
Well, Gershon was talking about AppleTalk connecting to things in another country, and the analogous thing in Bonjour works using DNS queries, which today let you find things in other countries. And this is the first time I plugged into this network, but if I can get it all working correctly, then I can actually show you discovering services that are back at Apple, even though I'm 1,000 miles away. So we're talking about browsing, and without dwelling on this too much, I'm not the first person to recognize the importance of being able to browse. There have been countless attempts to do this from lots of different companies. And I would say they've all failed to get any kind of ubiquitous traction in the marketplace. And I think they failed because they were not ruthless about keeping things simple. And one of the key insights that I learned from writing software that used AppleTalk is the entity discoverer on the network is the service, not hardware. It's very natural for human beings to think about discovering hardware, discovering devices. But then once you've discovered the device, well, what can you do with it? Well, now you need some protocol for like discovering its capabilities and attributes, and things get complicated. And if you turn that whole thing inside out and say, forget the device, I want to print. Who out there knows how to print for me? And all the devices that can do that raise their hand. You're not discovering the device, you're discovering the service. And that, it's amazing to me that AppleTalk got that right, and then everything that happened afterwards for about 2 decades got it wrong. Because it really is the simplifying assumption that makes this work. And I hope that some of the demos I show later will make that clear. There was a question at the back there.
Yeah, are all the aspects of the technology implementally deployable? I mean, do we need to change all the systems together, or is it possible that in one network we could have half of them doing it and half of them not doing it?
Are these technologies incrementally deployable? And the answer is absolutely yes. Any network printer that Microsoft has bought in the last year or two is doing this. So you have it running on the network, even though I'll bet most people are completely unaware of it. If you have people using Macs in the building, they will see the printers just show up in the print menu. If you install Bonjour for Windows, then you can use the printer setup wizard on Windows to find these printers. So there's certainly nothing that requires all of the machines to be upgraded in lockstep. Question back there?
The printer example is actually interesting. If I simply wanted something that would convert my PostScript file to PDF file, I don't care where the service is, right? It could be in Sweden. But I don't want my printer to be in Sweden. I want my printer to be as close to me as possible.
Yes.
So in some sense, I have to talk about the device here, right?
The question is that when you're printing, you do care about the location of the device because you care where you're going to get your printout. And that's true. But the thing that could be true, and I don't want to make this get too contrived, but you could have a print server that's hooked up to a USB printer, and what you care about is where the printer is and the paper that's going to come out of that. You know, what computer, what operating system, what software is running on the print server is not what you care about. You can care about the conceptual service of something that I can speak the LPR protocol to, or the IPP protocol, or whatever protocol it is your client speaks. It wants to find things that speak that protocol. So information about where am I going to get my printout is definitely useful information. I didn't mean to suggest that it wasn't, but when I press on with the examples, I hope it'll become clear, and at the end I'll try to leave time for some additional questions.
Yeah, let me suggest something on that. It is indeed very important that location of printers be known because it's a fundamental decision the user wants to make. But trying to cram everything like that into a discovery protocol, which is I think the point you're making, may be too much. Perhaps what we should do is kind of like a sieve. You find the printers, then you have a printer-specific protocol, which allows you to do a finer braid search for something based on properties that are relevant to printers, as opposed to cramming all that down into a generalized discovery protocol. Is that, for instance, the point you were trying to?
Yes. Gershon was making the point that a lot of these things can be done with application-specific protocols, and in terms of finding the capabilities of the printer, like can it do double-sided, can it do color, those things are often better described by a protocol that's designed for that job. You have a printing protocol anyway, so a lot of the feature negotiation for what printing can do naturally lives in that protocol. The other thing I would say, following the principle of simplicity here, is we can make very formal sort of database schema type descriptions where location is a semantic field. And as computer scientists, that seems very natural. It seems like the right technical solution. But then the people using it have to understand our database schema. And even if it's just a simple sort of, it's effectively rows and columns, but there is still something to be understood there about where data is supposed to go. And in my experience, if you have a name for something, humans will naturally give it a descriptive name. And if what's interesting about this printer is that it's the color printer on the 3rd floor by the copy room, then they'll call it 3rd floor copy room color printer. And that tells you what you need to know about it. It doesn't tell you what you need to know about it in a strict programmatic sense that you could write a database query, but it tells you what you need to know about it in the sense of a human being looking at a menu in a restaurant can read the descriptions and pick the thing they want.
I wasn't clear from your talking about addressing and naming that if this printer on the 3rd floor is on a separate subnet, how do I discover with this Bonjour protocol?
Okay, so I think maybe I should move on with the presentation because we're getting a lot of questions that are kind of foreshadowing things I want to talk about. And most of this talk is going to focus on the link local Bonjour because I think that's the area today that causes most grief for most users. But at the end, I will try to show some of the wide area stuff as well. So one of the observations that we made here was we've kind of agreed that all of these little devices are going to need link local addressing. They're going to need multicast DNS. A lot of them don't have much memory. If we could repurpose or make use of the functionality that's already there by virtue of multicast DNS, we can get service discovery as well almost for free. And that's where we get the DNS-based service discovery from. And by building the service discovery on DNS, in this case multicast DNS, that's how we get something that, having finished that design, it actually translates pretty cleanly back into the wide area unicast DNS world. So now we have service discovery semantics that work more or less exactly the same, on an isolated ad hoc network and on the global worldwide internet and on universities and schools and corporations and everything in between those two extremes. So my little sort of mental puzzle here was, I wonder what is the minimum amount of change we'd need to make in DNS to support service discovery. And the surprising result was actually none. We don't need to define any new query types or any new wildcard characters or any kind of modification, because the right pieces were already there in the DNS specification. They just hadn't been put together quite that way before. And those three facts are: DNS can return more than one result. If you have a multi-homed host and you look up its address, you get back a list of addresses. This is pretty standard. We have these things called PTR records, which are the things that are normally used for mapping from address to name. But in fact, a pointer is a pointer. It's a link from somewhere in the name tree to somewhere else in the name tree. And we have SRV records, which describe services instead of hosts. And one of the mistakes, I believe, in the original DNS is that when you look up a host name, what you get back is the IP address, but you don't get back any port number. So we end up with this assumption that every web server has to run on port 80. And when we look up host names like www.microsoft.com, that's not a host name, it's a service name, right? Nobody cares which piece of hardware they're connecting to. What they care about is they're getting the web page for Microsoft. It's a service name. But when you look that up in your web browser, the answer comes back, something, you guess the port, I'm not telling you. And that's just kind of a silly oversight. And I don't claim to have invented this. This is one of the things the AppleTalk name binding protocol didn't just give you the subnet number and the machine, it gave you the port number of the process on that machine that would offer you the service you wanted. And fortunately, the DNS guys did think of this, and they created SRV records a good 10 years ago. So they were just sitting there waiting for me to use. They're supported by the clients, they're supported by bind 8, bind 9, so I didn't have to invent anything new there. So there are three basic operations we want to support. We want to support registering or advertising a service, we want to support browsing, and we want to support resolving. And the reason those last two are separate is also an interesting point, and that's a point that a lot of discovery protocols get wrong. Browsing and using a service are two separate operations, and I'll make an example which I think makes it very clear. When you pick your default printer, that's an operation you may do once in a week or a month or a year. You may pick the default printer and never change it on your work machine. But printing to that printer is something that you may do every day. And in a world of dynamic addresses and DHCP, you can't assume the address stays the same all the time. So the user needs to browse and get a list of choices, and then you save their choice on disk in some persistent way. Every time they print, you then need to get that name back and say, tell me the address and port for this printer or this named service, and that can change over time. And protocols like SLP had no way to do that. SLP could browse and give you a list, and tomorrow if the IP address had changed, well, you had to browse and get the whole list again and then find the printer you wanted out of that list. And of course, you could do that programmatically without presenting UI to the user. But still, in terms of the network, it's an expensive operation to have to browse and find everything and then pick through yourself for the one you want, when you actually know what you want. You just want to tell the network, I'm looking for this service. Look that one up for me. So that's why we have a kind of three-phase protocol here. So this is how we browse to find services on the network that speak IPP. And that there's intentionally a sort of behavioral model here. We're not asking who will put ink on paper. We're asking who speaks IPP. Because if you've written an IPP client, it's willing to speak to devices that speak IPP. And you can imagine some hypothetical device in a legal office where you send it a PostScript file, and it doesn't print it on paper, it burns it to CD and creates a time-stamped archive of that document in electronic form. But from the point of view of your printing client, it's a thing that it can talk to on the network. It looks like a printer, it behaves like a printer, so from the software and protocol perspective, we're going to call that a printer. So we're looking for things that speak IPP. And the answer we get back are all DNS names of this format. The underscores and the underscore TCP are part of the naming convention for SRV records. We didn't invent that. It's a little bit odd, but there was really no reason to buck the established convention there, so we just went with it. Anywhere there was a good technology that already existed, we were happy to use it. We were not looking to invent things for the sake of inventing everything new. And the first label of each of those names is the user-friendly name that you display in the UI. Uppercase, lowercase, spaces, punctuation, UTF-8, kanji characters, whatever you like, up to 63 bytes long. And that 63 bytes is imposed by the DNS packet format. 63 bytes is long enough to give a reasonably descriptive name. And it's another one of the cases of making trade-offs for simplicity. Having limits like that means that very low-cost devices can implement this in known amounts of storage, and that's a limitation that we took on knowingly. Some people might say, I want to give my printer a name that's longer than 63 bytes, and if you can think of a really compelling reason why that's important, I'm sorry. I think in terms of screen real estate, it's difficult to make a UI that supports 200 character long names anyway, so that's one of the decisions that we made. Well, one of the decisions we inherited from DNS, and we were happy to inherit it. We thought we could live with 63 bytes as a reasonable name. It's a structured name, very much analogous to the old NBP names. They had name, type, and zone. And in the DNS world, well, we have name, we have type, and we have domain. And in this case, you see the domain is local. If that was something other than local, if it were Microsoft.com or building103.microsoft.com, that would then turn into a standard DNS query, which you could do with the NSLOOKUP command, and that's the answer to how this scales beyond the local network. Is we don't try to make multicast scale beyond the local network. We explicitly transition over to something that is more scalable on the wide area. Service types are opaque strings. They're normally human-readable strings because they're mnemonic and they help you know what it's doing, but they're just opaque identifiers. And one of the benefits here is that normally when you write some new application, you have to apply to IANA and get a port number. And there are only 65,000 TCP port numbers. And if every undergraduate in the world doing some programming project gets his own port number from IANA, well, we're going to run out. And these days, if you have a real commercial product and you ask IANA for a port number, they make you wait for more than a year before they'll give you one, just to see if you're really serious about it. With text strings, the namespace is more or less infinite. So it's first come, first served, have as many as you like. And when you run your software, you don't need a well-known port number anymore. You can listen on whatever port the operating system assigns to you because the service lookup gives the port number as well. So we really don't need well-known ports anymore for these services when you discover them using Bonjour, or indeed any directory service that lets you find out the port number as well as the IP address. A question there?
Is there an issue with configuring firewalls if you don't have a known port number?
Is there an issue with configuring firewalls? A lot of people think there is, and there is sort of an apparent issue. I think the reality is that configuring policies and firewalls based on port numbers was a convenient thing to do because it seemed to work. But if you've got some malicious hacker who wants to circumvent your firewall, well, they don't have to use the correct port for the protocol they're running. And in fact, these days, the way you get through firewalls is you use port 80. And pretty much we're going to get to the situation soon where every single protocol in the world runs on port 80 because that's the only one that goes through firewalls. And then we're going to have some higher layer filtering rules to look inside the packet and work out what is this? Is this something I want to allow? Is this something I not want to allow? And I fear that the generation that follows us is going to be taught the IP packet format in computer science classes, and there's going to be all these fields, and there's one in the middle that says must be 80, historical, can't remember why, carry on. And semantic filtering of who's allowed to traverse the firewall and why and what permissions you use has to be done cryptographically. In the long term, if you want to have something that really works, saying, well, if you're coming from port X, you must be trustworthy. I mean, if it's a low-numbered port below 1024, then, you must be one of the the sysadmins in the white lab coats. That view of, Unix systems before, normal users couldn't use ports below 1024. But now that everybody's got their own Linux machine on their desk, people still do like to filter on port numbers. I completely acknowledge that. But I think we're going to have to accept a move to something a bit more cryptographically secure and cryptographic end-to-end security as well. Because the firewall model, this was not supposed to be a security talk, but the firewall model does not reassure me. It's the sort of crispy on the outside, soft and chewy in the middle model, and once you penetrate the shell, there are no defenses inside. And I won't say any more about security right now, but I'd be happy to later. So,
excuse me, one question.
Yes.
So what served up all of those services? So when you did the request, where did those things come back from? The sales, marketing?
In the .local case,
Yeah.
it was multicast on the network. That DNS query was multicast. And every device that speaks the IPP protocol would send you back an answer. And all those answers are aggregated and displayed to the user.
I see. So it wasn't registered with the central DNS server inside of the...
In the .local case, no. In the Microsoft.com case, yes. And that becomes a standard DNS update, which is another standard IETF RFC protocol.
However, there could be information in caches sitting on various local entities that could get served back.
There are, you can have proxies that are answering on behalf of devices. We have, every printer at Apple is about 10 years old because we made these really, really reliable laser writers about 15 years ago and they're all still working. So we actually have proxies.
Blame me, my product.
They are just rock solid, they won't die. We have proxies that actually browse the network with AppleTalk, find the printers, talk to them over AppleTalk, ask them what their IP address is, and then turn around and advertise that. Because these printers do actually do LPR, they just predate Bonjour. So once you find the IP address, we advertise that there's a PostScript service on port 515 at this IP address, and that way all the desktop machines don't have to have AppleTalk turned on. And in the new Intel machines from Apple, there's a good chance, this decision hasn't been made yet, but there's a good chance they won't even have AppleTalk. So having something that will turn around and advertise these legacy devices is useful. And that's one of the things you can do with this technology is advertise proxies. The device does not have to answer for itself. Quick question there.
Are proxies how you do power management, say the device is in a power down mode or something?
Have you been reading the internet drafts? Yes, power management is done exactly that way. When a device wants to go into low power mode, it recursively uses Bonjour to find the sleep proxy service on the network. It pickles up its DNS records and hands them to the sleep proxy and says, answer these for me. And if somebody asks for the service record or the address record, send me a magic packet to wake me up. If somebody's just browsing, looking for PTR records, you can answer for me. But the moment they ask for the SRV record, you don't answer. You wake me up and I'll answer.
You just made me feel very good because I did that.
Oh, I didn't even know that. So very quickly, this is how the resolving phase works. So we know we want to use the printer called sales. We look up its SRV record. We look up its text record. We get back the port number and the target host where that service resides. And one of the nice things about DNS is you can put additional records in the packet. So the device responding kind of anticipates that we're going to want to know that address, so it sticks that in the packet as well, just so that we don't have to do another query to get it. And that one packet encapsulates all the information you need to know to connect to the service and use it. This has been around for 3 years now on Mac OS X, and it's available for Linux and Solaris and other platforms, and it's obviously available in Bonjour for Windows as well. Now, Gershwan was asking about what did AppleTalk get wrong, and I wouldn't put it in those terms, but one area where we've gone beyond what AppleTalk did was a lot of techniques to reduce chattiness. AppleTalk had a reputation for being chatty, maybe somewhat deserved, somewhat not deserved, but in any case, we didn't want people to say, oh, AppleTalk all over again. So we put a lot of work into techniques So for example, when you issue a query, if you've already found half the printers on the network, you include a list in the query that says, you guys don't answer, I've heard from you. Somebody else, if there's anybody else out there, that helps avoid systematic packet loss. If you've got an Ethernet switch that can hold 40 packets in its buffer and you do a query and everybody answers at the same time, the slow device always gets lost. So you can end up with protocols like UPnP that you always miss the slow device every time. You need a way to shut the fast guys up and give the slow guys a chance to answer until you've accumulated the full list. We don't keep pounding the network with queries. We have exponential backoff 1, 2, 4, 8 seconds up to an hour. When you're querying once an hour, you don't want to wait an hour to find things. So new devices coming online announce themselves. And that's not just powering on. To pass the Bonjour conformance test, the Ethernet hardware has to implement link state changes, which is quite common today but wasn't 5 years ago. So when you connect the cable, the device says, oh, new connectivity, get a DHCP address or not, announce services, so they show up within a few seconds. And timeliness is very important. And we also don't want to have a refresh button in the UI that the user has to keep clicking, so we're very strict about that. No refresh buttons, no quitting and relaunching. Everything is live all the time. And we have to do that in a way that's good to the network, right? We don't want what happened, sorry Gershran, but one of the common things people were told at Apple is don't leave the chooser open. You know, when you found your printer, close that window because you're hurting the network if you leave that window open. And with things like iTunes and so many applications, browsing all the time, we can't do that. We have to be able to do continuous ongoing browsers in a way that's gentle to the network. We have a bunch of features to make it timely in the opposite direction as well. So if you shut your machine down, it sends a goodbye packet and its services disappear from other clients. But what if you just yank the Ethernet cable? Well, to avoid polling, we have a long time to live of an hour or two. So then the problem is you might be seeing stale services show up. And we came up with this, I think, innovative solution to that, which is if you see a printer that's available on the network and then you try to print on it, your attempt to look up its address is going to fail. And we use that failure to basically call into doubt the records that led us to find that host name, and we requery for those records. And if we don't get an answer in a few seconds, we remove them from the list. And we also do this in a way that all the other devices on the network observe it as well. So the end user reaction, the human experience you get from this is you see the print, you go to print, and then when you print, you get an error that says printer not available. And you go back and look in the printer list, and it's gone. And you think, oh, somebody must have turned it off or unplugged it or something. I mean, the reality is they may have turned it off half an hour ago. But the important point is that the user has a wrong but internally consistent model to explain what they just saw. If they go back to the list and the thing is still there, then they start getting frustrated and banging the keyboard against the screen. If the thing disappears, okay, I've got to find out why this printer's gone, wander down the hall, find out who turned it off. Everybody else on the network sees this as well, so in fact only one person goes through this experience and everybody else gets the benefit of it. So we have a lot of things like that which give a really nice user experience at low cost to the network. Question there?
I have two questions. One is, will that expose some security issue? Because people can just fake this kind of...
Absolutely, yes. Okay. The question is about security issues in this, and all of this, the protocol design is predicated on having a group of devices that are mutually trusting. If you want to work in an environment where you have hostile adversaries that are trying to sabotage what you're doing, then you need some kind of cryptographic security. And there are lower layers that can provide that. If you're using wireless, you can use a web key or something to create a community of people who are mutually trusted. You can use IPsec encryption to sign the packets so that you can distrust imposters who don't have the right cryptographic credentials. But the nature of this technology is it's kind of the strangers meeting on a train type approach. And actually that's more than just an analogy, that's actually real. One of the things that Mac users are in a habit of doing, and I'm not sure I should endorse this, but when they fly on aeroplanes, they create a little wireless network. And in iChat, you see the other people on your flight. and it really is strangers who've never met before saying, oh, hi, and you see people. Maybe a better example is at conferences and IETF meetings and things like that. You have your normal instant messenger buddy list of all the buddies that you've manually added, but you have this other buddy window, which is people near me. And they may be people you know, people you don't know, people you've heard of, but there is very much a sense of trust. If somebody wants to disrupt that, then you go over to using other mechanisms that do have trust, and they're not as easy to use.
Okay, actually I have a second question. So, as you mentioned that all the other clients on the network will actually monitoring this kind of failure
Yes.
cases, right? What if my machine is sleeping right now, and I turn on the machine, resume from hibernation, and I try to...
What happens if your machine has been sleeping? Well, the simple answer there is when it's asleep, it knows it's not seeing what's going on the network. So when you wake it up from sleep, it issues the queries it needs to find out the current state.
But the list, the service list was persisted, right? For example, the printers available.
Everything in the service list is cached with a time to live, and there is no guarantee that everything in the service list is absolutely 100% accurate to the microsecond, because that would require an infinite amount of traffic. So what the design goal is that the service list you see should be very close to being correct and should be continuously converging to correctness over time. So when any change happens, you should find out about that change within some reasonable time window, and reasonable depends on the context of what you're doing, and it also depends on packet loss and other things, because there are no guarantees in networking. Everything becomes a case of, well, if you lose this packet and that packet and that packet, you still want to guarantee that you will converge to correctness eventually, and the question is how long that takes.
So do you mean that each client has to for each type of service, it has to do the discovery or browsing, as you mentioned, periodically? Because I cannot trust what even...
Well, let me take this. I'll try to answer this question quickly, and then I'll press on, because I would like to show some of the demos before we finish. Yes. Everything in networking has to deal with failures, right? Even if you browse, you find the service, you find the host, you find the IP address, you find the port, somebody yanks the Ethernet cable, your TCP connection is going to fail. So any piece of networking software has to be coded to handle failures like that. And we can't avoid that. There's no way to guarantee. A lot of protocols like ATM tried to give guarantees, and you fundamentally can't give guarantees in a world where the user can unplug the cable. And in a world of wireless networking with microwave ovens and things, this is why wireless ATM never took off, because they'd set such a high bar in terms of guarantees that physics wouldn't let them meet those guarantees. IP, ironically, basically gives no guarantees at all, which is like, give us a packet and we'll try to deliver it some of the time if we feel like it. And the endpoints have got to expect that and retransmit and have the mechanisms to handle that. That's why IP works so well over networks like wireless that fundamentally are lossy networks. So it's one of these less is more kind of situations. So this is actually where I was planning to do some of my demos. So I've got a bag full of stuff here, and these are all, I think all of these are third-party products. These are not Apple products, and one of the things that's very exciting for me is seeing these products in reality, because anybody can do a rehearsed demo on stage and make things look good, but that's not what motivates me. What motivates me is knowing that millions of people all over the world are actually having these experiences for real day to day with products that they buy. One of the times at Apple when I was giving a talk, the guys organizing the presentation looked at me and said, what do you think you're doing, right? You're not Steve Jobs. You don't have 3 hours to set up. And my answer to them was, well, if it takes me 3 hours to set up, then I've kind of like not succeeded in what I'm trying to do. The whole point of this is that I should, let's hope it doesn't let me down today, I should just be able to grab stuff out of the bag and plug it together and have it all work without any preparation. So In fact, Gershran, maybe you could,
I won't take any blame.
Could you plug one of those into the back of my laptop?
Back of your what?
The laptop up there, if it'll reach. Can you get that out? It's sometimes a little bit difficult to get it out. Will that reach? So this is one of my favorites. This is a camera that Axis makes.
Where do you intend taking this? It's pretty short.
Well, let's see if it'll have to go there. I thought it had a longer cable. I have So one of the differences that's always, one of the benefits of USB that's always cited is that it provides power. And I'm very happy that power over Ethernet is now finally becoming mainstream. So this little $99 Ethernet hub from Netgear actually provides power to the device as well over the Ethernet cable. And before I plug this in, let's forgot to plug that in.
I'll get out of your way.
No, I don't think so. So this is Safari, Apple's web browser, and Safari has this little bookmark item here called Bonjour, and if this works according to plan now, I plug this into the camera, and if any of you guys have tried setting up a network camera or a network printer or anything that does IP but doesn't have a screen and keyboard, you probably have the experience of just how much grief you have. And the manuals go through, type this funny ARP command or type this ping command 3 times, or, you know, if you're a networking person, you just end up looking with TCP dump and trying to work out what's going on. And this is obviously not the way to sell a consumer product. This camera runs Linux. You know, you can telnet to this and run Emacs on it and edit the files. And it does.
Are you showing the right port there? You're not link or something?
Let me. Not plugged in. I like that. This might be a
Bad cable.
No, I think. Now, the crossover cable is not the problem. The Macs do auto crossover. I know what the problem is here. I forgot to plug the power in and it went to sleep. And there is, in fact, I know there's a bug on this old PowerBook hardware that sometimes when you wake from sleep, the Ethernet chip doesn't get reset. And now it won't even let me sleep it. So I might just have to reboot this. Sorry about that. Well,
Stuart, I noticed there's no link light on the
I know. Yeah, the Mac side was saying no cable, and the hub has no link. And I've had this happen once or twice before. Just sometimes the Ethernet chip doesn't power on again.
Stuart?
Yep.
While you're waiting for the
you answer a question for me?
Sure.
I note that link level addressing is an RFC, but MDNS is not. Can you give us a status on the standardization of MDNS?
Yes. MDNS and DNS Service Discovery are individual submissions, and it's possible that sometime in the near future they might be published as experimental RFCs or informational RFCs. Realistically, the chance of them being IETF standards is pretty slim, because it took us 5 years to... The IETF is very democratic, and sometimes I think it's too democratic, that anybody more or less has a veto over anything they think is a bad idea. And if you take any group of 5,000 people, there's always somebody who thinks that something is a bad idea. And the link local addressing is pick a random number, ARP for it. And if you get an answer, pick a different one. And it took us 5 years of just incredibly excruciating wrangling to get that done. And the multicast DNS it's simple, but it's not that simple. And just people always, if there's two ways of doing something, you'll get people on both sides. And sometimes it doesn't matter which you pick, you just have to pick one.
Okay.
But sometimes...
You have Ethernet.
Oh, good, okay. And some people who are deliberately sabotaging the process, when it looks like the consensus is going one way, they'll deliberately argue the other side to keep the seesaw balanced. Okay, so I plug the camera in, and Axis 211 shows up, and I double-click that, and I have to delete my Microsoft proxy from my settings. Think. Turn that off. So I don't know what IP address this camera has, and I don't care, because it advertised that it speaks HTTP, and now I'm connected to it. And another nice thing this camera does is, so being able to see things in a web browser is pretty nice, but it's a camera. And we have native formats for doing video, and everything is a web page. It's not really very pleasing from a computer science standpoint, although it is useful from a pragmatic standpoint. The web browser has kind of become like the VT100 serial terminal. It's the kind of de facto way you connect to a piece of hardware. But since this is a camera, it also generates RTP streams over UDP, and QuickTime Player will browse for advertised RTTP services. So again, without knowing the address or what to type or anything, I just select it, and QuickTime is now showing the raw RTP coming from the camera. So if you want to build some home surveillance software or something like that, these things exist today. There's EvoCam and Security Spy and a whole bunch of things. They're all full of typing IP addresses in. And you can automate this by just having a menu and picking the cameras from the list. It doesn't necessarily substitute for having manual configuration, but it's definitely a very welcome addition to having manual configuration. One of the things I wanted to show you guys today, if you've ever been to conferences or things like that where they have a terminal room with printers, you're probably familiar with the difficulty you have of configuring your machine to print on a network printer. I either need a long cable or I need to move the printer. Moving the printer might be. Yes, and where's the Ethernet socket? Is it around there? So, So we want to print this. Well, we don't have a printer. So let's let the printer power up, and we'll see what happens. While that's warming up, in the last few minutes, let me show you some of the other things I have here. This is another one of the Axis cameras. This also runs Linux, but this is even smaller than the other one. This is their new model they're bringing out just this month. This is a Linux machine, so that's pretty cute. The printer guys were among the first to adopt this. This is a little print server that goes in the parallel port and then advertises Bonjour printing service over the Ethernet. There's HP's equivalent of the same thing. This was one of my favorites. This one is IO Gear. That's a print server. The print server is actually smaller than its own power brick. This needs power over Ethernet. Ethernet in one side, USB out to the printer on the other side. This thing I love. You're probably familiar with the USB to serial adapters for all the computers that don't have serial ports anymore. Well, this is like that, but this is an Ethernet to serial adapter. And they love these in data centers and places like that. You've got all the rack mount equipment with the serial ports on the back, and you would normally have to have this great waterfall of serial cables connecting to your terminal concentrator or something for you to configure these things at boot time and access the console. You just plug these in, and they hook up to the Ethernet, and now you can telnet to the serial ports of these various devices. So the guy who makes this came to one of our workshops at Apple. Well, maybe that's not going to work as I hoped. The guy who makes this came to our workshop, and I'm proudly talking about our code, and it's only 100K, and in this era of multi-megabyte bloated applications, I'm feeling pretty smug about that. And he says, no, you don't get it. This has got 16K of flash memory. And in that 16K, well, 9K of it is the HTML pages that I serve up for the user interface, and that leaves 7K. And in the 7K, I've got Ethernet driver, ARP, IP, UDP, TCP, DHCP client, DNS client, web server, telnet server, serial port driver, and you've got 800 bytes left to do Bonjour. So we kind of go to the whiteboard and do a bit of a thought experiment about what could we possibly eliminate. All the fancy options are going away. But one of the things that makes TCP an interesting protocol is that you can do an incredibly stupid TCP implementation that sends one packet and waits for an ACK before it sends the next one, and it won't perform very well. But you can take that and connect it to the most sophisticated TCP experimental implementation on the planet, and they will talk to each other. And that's a pretty remarkable property for that protocol. It'll work on from modems to gigabit links. It'll work from microsecond local round-trip latencies to half a second or a second delay from one side of the planet to the other. And for a single protocol to scale to those extremes is really remarkable. And I tried to design a protocol that would have those same properties. And he managed to fit in 800 bytes of assembly code a compliant multicast DNS responder in this. One of the things he uses is, he has a pre-prepared packet in memory. This is what I know. These are all the DNS records. You ask it a question that matches one of those, it says, this is what I know. You sort it out. So he did some simplifications, but you plug this in, it advertises telnet service, and it shows up in the terminal program in OS X as an advertised telnet service, and you can browse from the menu and connect to it. And one other thing that I really like, this is mine from home actually, and I brought it in. This is a Roku Soundbridge, and it's a little music player. And if any of you have tried using these sort of home media things that connect to your hi-fi, you've probably had the experience that they're pretty difficult to get working. And let's see how hard this is. So I need speakers, I need audio.
Stuart, is the Windows Bonjour out of beta now?
Yes, it is.
Is that what makes the iTunes on Windows share?
That's right. If you're running iTunes on Windows, you're already running Bonjour on your Windows machine. Okay, I'm not going to worry about trying to troubleshoot this printer right now, but let's plug this into here instead. And so one thing I'd hope people would take away from this is, you see me plugging all this stuff in. It was on? Okay. You see me plugging all this stuff in, and apart from the printer, which just maybe an older printer, I don't know, I plug the stuff in, I plug in the camera, and it works. And if your reaction is, well, yes, of course, well, that's the right reaction. But the reality today is, if you bought some new piece of this is if you normally buy some piece of equipment, you're going to expect to spend half an hour or an hour trying to get the thing set up and working. And I hope I'm not going to spend that right now. But all right, I'll try this one more time and take any last questions. Yes, one at the back there.
Yeah, just one business question, I think.
Yes.
I mean, you're showing a lot of devices that obviously now support Bonjour. I mean, what did, one or two things that Apple did absolutely right that made it broadly adopted by the industry, by the device industry?
The question was, how would I explain the success of Bonjour? And I think what Apple did right was we made it open source, we made the specifications public, and we actually encouraged other people to do competing implementations. There's a version of multicast DNS written in pure Java. There's one written in C# from Novell. There is one that just came out last month called Avahi on Linux. And instead of seeing these people as competitors, I think we see some friendly rivalry trying to make the best software, but we really see them as partners in creating this ecosystem of compatible products. And so that's what Apple did right. Apple hasn't done everything right. Apple has been slow to evangelize this, and the trademark problems didn't help us there. So certainly within the Mac community, every Mac developer knows what Bonjour is. Pretty much every Mac user knows what Bonjour is. If you're making a piece of hardware or software for the Mac that does networking, it doesn't do Bonjour, people will just laugh at you. It'd be like producing a piece of software that didn't work with the mouse or something. But you don't have to step very far outside the Macintosh community to encounter people who've never heard of this at all. I just came back from Scotland. I was at an ISO standards meeting for home networking for control protocols like lighting and heating and air conditioning. And they were about to basically say they adopt UPnP, not really because they liked UPnP, but because as far as they were concerned, it was the only game in town. And about a week before that meeting, somebody said to them, well, why not Bonjour? And they said, what's that? And they called me, and I ended up flying over to give this presentation, and they had never heard of it. So in that sense, we could definitely be doing a better job, and that's why I give presentations like this, and that's why I did the O'Reilly book, because I don't want this to be AppleTalk 2, right? This is not supposed to be, this thing that's only for Macs, it's only for iChat, it's only for iTunes. I actually want to do something that's like TCPIP, and I'm fortunate that Apple gives me enough free rein to do something that is open and benefits other people as well as just Apple. So it is literally 12 o'clock, so maybe we should probably wrap up there, but I'll be around here. I'm happy to talk to people offline afterwards. Thank you all for coming.